which is on custom forces, which is a subject that, at least in the other session, kept coming up, and I kept saying, oh, wait till the talk this afternoon, you'll hear all about it. So one of the things I mentioned earlier was that we wanted OpenMM to be very, very flexible and extensible, because we know that we ourselves can, we're a very small development group. We have 2 core developers. We can't implement ourselves every feature anyone's ever going to want. So we do provide all these standard forces that cover the most widely used functions that come up in standard force fields: harmonic bond force, harmonic angle force, non-bonded force, etc. But what if you need something that's not on this list? Our first thought is, okay, well, we'll have this plugin architecture, and people can write plugins to add new types of forces. And we very quickly found that this wasn't going to be sufficient for everyone's needs, because it's actually a lot of work to write a plugin. And if you want that plugin to run on a GPU, that means knowing how to write GPU code, which most biologists don't. And so, yes, it's an option, but for a lot of people, it's not a very good option, and we wanted something that would be much more accessible. So what we came up with is this idea of custom forces, with the goal being to provide some of the flexibility of a plugin with most of the simplicity of a standard force. And the idea behind it is very simple. You specify what the energy function is, and we do everything else. And when I say specify the energy function, I mean literally you give us, just as a text string, an algebraic expression, and we'll take care of it from there. So in this example here, we're saying we want a custom non-bonded force, and we give a mathematical expression that is the energy of interaction between 2 particles as a function of the distance r between them. And in this case, we've got some constants in there, which you'll be able to set. But we take that and we do everything else. Actually, we have not just one type of custom force, but we have lots of different custom force classes, each one specialized for implementing a different type of force. So custom bond force is a very simple one. It defines bonded interactions between pairs of 2 particles, so like harmonic bond force, except that it doesn't have to be harmonic. You give us the energy between each pair of particles as a function of the distance. We take care of the rest. Custom angle force is very similar, except it's an interaction between 3 particles as a function of the angle formed by those 3 particles. Likewise, custom torsion force is a interaction between 4 particles. You give us a function of the dihedral angle. We turn that into a force. Custom external force is actually a very useful one that you'll see an example of shortly. This is basically a force that is applied independently to every particle, and it can be a function of the position of each particle. The custom non-bonded force you already saw an example of, but it's basically a non-bonded force, so every particle interacts with every other particle. The interaction between each pair of particles is a function of the distance between them. You pick what the function should be. Custom compound bond force is actually a superset of all the other bonded forces that you've already seen. So it can be an interaction between an arbitrary number of particles, 2, 3, 4, 5, however many you want. And it can depend on all these different internal and external degrees of freedom. So the position of each particle, the distance between any pair of those particles, any angle, any dihedral, and you can write a completely custom function of all those different variables that defines the energy of each bonded group of atoms. And then we've got a few more complicated ones. Custom GB force supports various implicit solvent models. It's very complicated to use, but that's only because implicit solvent models are very complicated, and it might take you a dozen lines of code to implement an implicit solvent model. Only if you were to take the same implicit solvent model and implement it just by writing GPU code, it would take you 1,000 lines of GPU code. So it's complicated, but it just because it's letting you do something very, very complicated in a very small amount of code. And custom H-bond force is similarly a very flexible one that can be used to implement a pretty wide range of hydrogen bonding models. So let's take a look at this. So suppose you want to put harmonic restraints on particular atoms in your system. Now, this is a pretty standard thing to do in MD, and most MD packages have a feature to apply harmonic restraints to the atoms in your system. Turns out that OpenMM doesn't have such a feature because it doesn't need one. So here we basically implement that feature ourselves in 4 lines of code. So this is assuming you want, this sort of function. So this is just a harmonic restraint that binds a particular particle whose coordinates are x, y, z to some reference position that I call x naught, y naught, z naught. And I just say that I want the energy of this interaction to be harmonic in the distance between the particle and its reference position. So as it tries to go far away, it'll get pulled back. So what do? I create a custom external force here. And I just give it a text string, which if you compare this to this, you will see it is quite literally exactly the same mathematical expression. So just 10 times x minus x naught squared, y minus y naught squared, z minus z naught squared. OK, we need to tell it, oh, by the way, x naught, y naught, z naught, those are per particle parameters. So I'm going to define a value of those for each particle. So we just call force add per particle parameter. And now we're all done. We can use this force now exactly like we would use any other force object, just as you would use the built-in forces. You want to add a particle to say, OK, we want to apply this particular restraining force to a particle. So we say force add particle, and we give it the index of the particle that we want to apply it to. And we give it just in order the value of our per particle parameters. So x naught is 0, y naught is 1, z naught is negative 0.5. We specified that those are in nanometers. We don't actually say here what type of quantity this is. We don't say that this is a distance, but OpenMM does know that, OK, this is a distance. Therefore, if I had said angstroms here, it would have automatically put in the factor of 10 to convert it to the standard OpenMM unit. So it knows, OK, you've given me a distance. I should convert that to the proper distance units. And you can use this just like you would use any other force object. Let's give another example of something you might want to use this for. So Lennard-Jones combining rules. Lennard-Jones is a very widely used potential function for representing van der Waals interactions. This is the form of it. Exact form doesn't matter. But the important thing is that it's got these 2 parameters in it, epsilon and sigma. And this is the interaction between 2 atoms. But we don't want to specify a value of epsilon and a value of sigma for every single possible pair of atoms, because that becomes an n-squared matrix. It's huge. Instead, what people do is you specify an epsilon and a sigma for every atom. But this doesn't have 2 different epsilons and sigmas. It has 1. So what we need is a combining rule that says, OK, given the epsilons for your 2 atoms, what epsilon should we use in this expression? Given the sigmas for the 2 atoms, what sigma should we use in this expression? And the non-bonded force class uses a particular combining rule called the Lorentz-Berthelot combining rule. And it's just this. It says, take the geometric mean of the epsilons and the arithmetic mean of the sigmas. That's what's built into it, and this is a very widely used choice. Like Amber force field uses this combining rule, etc. However, there are others. For example, the OPLS potential function uses the Jorgensen combining rules, which says you take the geometric average of the epsilons, but also take the geometric average of the sigmas, not the arithmetic average. So what do you do if you want to implement the OPLS potential function using OpenMM? Well, OK, one option would be to say, OK, this is a really tiny difference. It's going to make negligible difference for most purposes. Don't worry about it. Just use non-bonded force, and you'll get the Lorentz-Berthelot combining rules, and that's fine. Might be true. It probably won't make much difference. But you don't have to do that. Another option is to say, use a custom non-bonded force. We can just give it this expression, which is just exactly the Lennard-Jones function, 4 times epsilon, sigma over r to the 12th, sigma over r to the 6th. And you can also then say where epsilon is square root of epsilon 1 times epsilon 2, sigma is the square root of sigma 1 times sigma 2. we have to tell it that we're using, I'll get to that, I'll explain. We have to tell it that we're using 2 per particle parameters called eps and sig, and then we can add our particles and give it the values of those 2 parameters, eps and sig, for each particle. Now what you're probably saying is that, okay, wait, what's going on with eps and eps1 and eps2 and all that? So you give it these per particle parameters called eps and sig. What actually appears, though, in your expression here is going to be those variables with 1 and 2 appended to them. So eps1 means the value of the eps parameter for particle 1. Oh, and just the thing I was about to say was that, so you can give like these sub-expressions, you give a semicolon. So you can say like eps here and then semicolon and then define what we mean by eps. And you can give like as many like sub-expressions as you want there just to make your equations come out cleaner. Makes no difference whatsoever to the performance or anything. It's no different than if you had actually said square root of eps1 times eps2 there. It's just to make it easier to write things, especially like when sig is going to appear more than once there. Just some other features that custom forces have. You also can have global parameters where you just have a single value, well, as it suggests, globally, and so not per bond or per particle. The main advantage of these is that they're very cheap to change at any time. It is possible to change the per particle ones, but it's a bit more expensive to do it, whereas it's really cheap to change the global ones. So, not all, but some custom forces support tabulated functions, where you can just give us a series of values that you've tabulated, we'll fit a spline through them, and then that just becomes another function that you can use in your expression wherever you want. Oh, I'm sorry. This slide is out of date. It's also supported by custom compound bond force. So, yeah. So if you want it in bonded forces, that's the one to use for that. A bit about performance, you might be thinking, wow, isn't this like, it's got to evaluate this string, isn't that going to be really slow? Answer is actually no. And that's because we do a whole lot of magic here. You know, you just see the string, but what happens is, well, first of all, we run it through an algebraic expression parser and convert it to an abstract syntax tree. And then we do an analytic differentiation to get the derivative of it, because we need that for the force. And then we do a whole bunch of optimizations on both those expressions to try to simplify them as much as we can. And then we generate OpenCL or CUDA code to evaluate that expression. And then we take that code and stick it into the middle of a kernel and send that kernel down to the compiler. And so what actually ends up happening is that you end up with just a GPU kernel that runs at the same speed as any other GPU kernel. It just happens to have your expression embedded in it. And so it actually is very little performance difference from the standard forces. That's true for OpenCL and CUDA. Reference platform actually uses an interpreter, so on reference platform, it'll be a lot slower. But if you're using reference platform, you probably don't care about performance. So anyway. So let's take a look at a concrete example of it. And this is a spherical potential. So this is simulating a sphere of water. And we want this water to be contained inside a harmonic potential. So it's flat out to a certain radius and then gives a harmonic potential beyond that so that your water can't drift away. And this script is almost identical to the ones that you've seen before. The only difference is these 4 lines right here in the middle, where we create a custom external force. So we're going to create a custom external force. So you remember, this is the one that is applied separately to every atom based on the coordinates of that atom. We are going to say that the value of it is just this expression. So a spring constant times max 0, r minus 1 squared. So if the radius is less than 1, then this will be 0. So out to a radius of 1, it'll just be flat. And then when r is greater than 1, it'll be quadratic in how far it is beyond 1. And we say, oh, by the way, r is just the distance from the origin, square root of x squared plus y squared plus z squared. So we create this function. We're going to loop over the particles, and we are going to call force.addParticle for every one. Like I said before, you can apply the force to one particle, a subset of particles, all particles, whatever you want. In this case, we want to apply it to all particles. So we are just looping over every particle. and we just give it the index of each particle. And there are no per particle parameters in this case, so we just give it an empty tuple here for the list of parameters. And we add the force to our system. And that is all you do. And you do this, and you now have a spherical potential to contain all your water molecules. So now you get to try it out. If you go to the exercises directory that it gave you, you will find the script called watersphere.py. And if you run it, it will generate a PDB file. And then we want you to try to load that PDB file into VMD so you can look at it and see that, yes, it really is containing it inside the sphere. And then here are a couple of things to try and see what happens. So it looked like a lot of you have managed to do these things. So can someone tell me what did you change in the script to change the radius to 2 nanometers? Yep, and then it's, so you just change it, and then it's flat out to radius of 2. And what about for the second question? What happened when you changed the temperature? Oh, can anyone successfully do the second one?
I did 100K.
100K, and what happened?
Just for fun, and then the water molecules just came together and
Yep.
relaxed all like near each other, minimal movement.
But not an ice block. This is one of the earlier comments.
Yeah.
Right. So
So is
it accurate to say that because of the approximations, you would not expect to get a proper ice crystal?
Ooh, is Li Peng here? No? He can tell you all about the about the phase behavior of all sorts of different water models. Definitely at 300 Kelvin, you expect it to be water. So if you have 300 Kelvin, you don't expect it to fill the sphere. You expect it to condense into a little droplet. Now, if you had infinite time and space for it to diffuse out to, eventually water molecules would evaporate away. But that won't happen here because it can't evaporate away. It's contained. So if you do it at 300 Kelvin, you just get a little droplet. And in fact, if you then change your sphere radius, you won't notice any difference. Whereas when, so by default, I think, default we have it at what? 1,000 Kelvin, right? So it's, superheated steam, blows out instantly, fills the whole thing. Now, if you go down to 100 Kelvin, I think at that temperature you would expect to see it freeze. Certainly, if it were a good water model, you would. Tip 3P is not a good water model outside. I mean,
is very slow.
Yeah.
It takes a long time. So if you cool it to 100 Kelvin, it'll just quench to amorphous ice, which probably would happen if you did that experiment.
Right.
Cool it very, very fast.
Right. But also, aside from that, Tip 3P was really designed for biomolecules at room temperature, and I don't think its phase behavior when you get very far from that is too accurate. Unlike, say, Li Peng's really awesome water model that actually gives excellent phase behavior over a huge range of temperatures. Anyway, that's just a way to see that the custom force is really working. Just want to talk about one more feature. Just as we have custom forces, we also have custom integrators, because there are a ton of different integration algorithms out there, and it's actually an active field of research. People are constantly coming up with new ones. And so we have this class called custom integrator, which allows you to invent new integration algorithms. The way you use it is that you define your algorithm as just a series of steps, completely arbitrary what those steps are. And each step can be defined by a mathematical expression that you give it. And it's flexible enough, it can do a pretty wide range of different integrators, deterministic, stochastic, certainly multiple time step ones like RESPA, metropolized algorithms, big range of different integrators. And let me just give you a very simple example. So velocity Verlet. The Verlet algorithm, the Verlet integrator that's in OpenMM is a leapfrog Verlet. Velocity Verlet is just almost the same thing, just a slight variation on that algorithm. But it just makes a nice simple example to show how you would use it. So we create a custom integrator. We tell it that we have a time step of 1 femtosecond. That looks exactly like you were using a Verlet integrator. But now we have to tell it what algorithm to use. And the way we do it is by calling add compute per DOF. So this is saying we're going to do a computation. This computation is defined by a particular mathematical expression, And that expression should be evaluated once for every degree of freedom. So every x, y, or z coordinate of an atom. And it's going to consist of 3 steps. So first step, we are going to be computing a new value for the velocity of this particular degree of freedom. And this is the expression to evaluate. This is an update to the current velocity, so v appears in here too. But it also knows about a bunch of other variables, like dt is the time step, F is the force acting on this particular degree of freedom, and m is the mass of this atom. Then our second step, so that's our velocity update. Then we have a position update, where we update x goes to x plus dt times the velocity. And finally, another velocity update. So if you're not familiar with the Verlet algorithm, don't worry too much about the details. But basically, the important thing is just that you can, this looks almost exactly like the pseudocode or just the equations you would write down if you were just sketching out what this algorithm is. And you basically just turn it into a series of function calls. This line looks exactly the same as this one, but there's a catch. F, the force, is a function of the positions. In the second step, we just changed the particles, the positions. We moved them. So the force here clearly is not the same force here. And you don't have to tell it that. It'll figure it out. It will say, oh, I see that the positions just changed. I know that the forces depend on the positions. Therefore, I know I need to recalculate the forces here. And it's smart enough, it'll just do that automatically. You can also provide additional variables. Here we're just setting the built-in variables, velocity and position. But you can define arbitrary other variables that you want. And those variables can be either global variables that have one value, or they can be per degree of freedom variables. So suppose that you wanted to have to compute the force here, and then you change the positions, and then you want something that depends both on, say, the current forces and also what the forces were. No problem. You'll just stick another step in here that will compute the value of your per degree of freedom variable and set it equal to f. So now you've copied f out into another variable, and then this step could depend both on f and your saved f. In this particular example, I'm only using compute per DOF, but there are other types of steps. There are steps that are just computed once to calculate a global quantity. So just you give an expression that's just computed once that only depends on global variables. You can have ones where you give it a per degree of freedom variable, which it evaluates for every degree of freedom and then sums those and sticks the sum into a global variable. And there's a few other specialized ones, like for evaluating constraints. So this is just a very simple example, but just to give you the sense of what you can do with this and how easy it is to define entirely new integration algorithms.